So welcome back. Let us continue our discussion on cubic point groups. So we have seen in cubic point groups how uh, the closed regular polyhedrons, actually there are 5 types of those, and then they all form different types of cubic point groups. So let us try to list them now. So the first one in the category is TD, and the symmetry operations I'm going to list for TD point group. So example is, we have already seen and worked example for this one is a famous methane molecule, tetrahedral, right? Now there are 8 C3 operations, then we have 3 C2s and 6 S4s and 6 sigma Ds. The total number of operations are 24. So we call this as, okay, somehow order of the group as 24, which is total number of elements, not the group elements as we have already discussed. Or in this case, we can say total number of symmetry operations. So you can see that it's a very large number, so it's a highly symmetric point group. Now the second is tetrahedral, and then we have octahedral, which is OH. Let us also list down, we can see the example as AB6, E, 8 C3s, then we have 6 C2s, 6 C4s will be there, and 3 additional C2 primes will be there. We have I, 6 S4. So as you can see that there is large number and it is difficult to remember all the symmetry operations. So unless you actually draw the molecule and try to identify all the symmetry operations. So let me go there. 8 S6, then you have 3 sigma H and 6 sigma D. Okay, and the order of the group is also denoted by H, is 48 here. Okay, next in cubic point group is icosahedron, denoted by IH. So the example here includes we have B12 H12 2 minus ion, which takes up the IH. So I'm not going to cover the shape again. So we already know the shape of the icosahedron. So another example, another famous example is C60, which is also called as buckyball. It is not a regular polyhedron because here you have alternating pentagon and hexagon faces, right? So we all know the structure of Buckminster fullerene. So C60 buckyball, it is not a regular polyhedron, but still it forms under IH point group. So let's see the number of symmetry elements, which is actually very huge in this, highest for a symmetry point group actually. 12C5, 12C52, 20C3. So we'll come back to this later, why we can combine certain set of operations into one number. So, and then for example, typically we have been seeing that C3 and C3 square can be combined as one set of operations, and then we can write it as 2C3, right? But in this case, C5 and C5 square belong to something called as different class. Okay, so these two actually form different class, and hence they are listed as separately. We will come back to it, what is a class, once we finish the point group identification. Okay, so 15C2 I, 12S10, 20S6, 15 sigmas, and 12S10 cube. So order of the group is 120. So this is the highest order symmetry point group, only after I think C infinity V and D infinity H, where H is infinity actually, because you have infinity number of elements. So after this, the highest order point group is icosahedron IH, and the examples we have already discussed. Okay, so now you can see that how there are different type of point groups available. So let us again summarize them. So summary of point groups. So we have seen that we had non-rotational, we had single axis rotational, where there is only one rotational axis. Then we had dihedral, then we had SN, and finally we had cubic, right? So non-rotational included C1, CS, CI. Single axis rotational included CN, CNV, CNH, and C infinity V. Dihedral included DN. So these symbols are called as Schoenflies symbols of point groups. We will see how to classify different molecules into these point groups depending on what symmetry operations are present. So DNH, DND, and what else was there? DNH, DND, and DN. Yeah, that's all. And then we have SN, and cubic we had seen TD, OH, IH. So actually cubic had more point groups. So let us also see here itself. So if you remove sigma out of these three, so minus sigma, then you will get corresponding T, O, and I point groups. So you can see that T, O, and I point groups are subsets of TD, OH, and IH point groups. So T is a subset of TD. Basically TD, if you remove sigma, you will end up in T. OH, if you remove sigma, you will end up in O. IH, if you remove sigma, you will end up in I. So they have little less symmetry, number of symmetry operations, or lower order as compared to this. Now, and then one more is there. So if you add sigma H to T, you will end up in TH point group. So you have 7 1, 2, 3, 4, 5, 6, and 7 point groups in this category. Okay, so I will list them all here. So you have T, O, I, and TH. Okay, so I hope this is clear. These are all the point groups that we have. Now, how do we classify these a given molecule into this? And it is not easy because we have to list down all the operations and then we have to check each of this whether it belongs to a particular point group or that point group or this point group. So there is a nicely made uh, flow chart. Let us look at this flow chart. It is available in many books, so but I have adapted with my understanding. I have adapted slightly differently, but then let's see. I mean, you can see different versions of it, but do not worry, they all end up in same classification of point group. So let's start with, so you're starting with the molecular structure, and you ask yourself whether the molecule is linear. Okay, so in a flow chart we typically ask questions, and then depending on if it is yes or no, we go to different sites, right? So if it is a yes, then what happens, and if it is a no, then what happens? If the molecule is linear, let's say if the molecule is, say, yes, the molecule is linear, does it have I? That is my next question. If the molecule is linear, then whether it is centrosymmetric, yes, leads to D infinity H point group, and no leads to C infinity B point group. So that is easy. Linear I, yes, yes, D infinity H. Linear yes, I no, C infinity B point group. Now linear no. Then you have, does the molecule contain two or more C3 axis? Okay. So C3 axes are present, but one C3 axis, two or more. Okay. So if it is two or more, you go to yes, question mark here. If it is a yes, then your next question is, and these have to be unique. Okay. So C3 axes have to be unique. Now next is two or more unique C5 axis. Does it have it? If it is a yes, then you ask again whether the molecule has an inversion center. So I understand that it is becoming very messy, but then as you practice it, I think it will become very clear. Then you assign it as IH. If it is a no, you assign it as the subset I. Okay. Now, if there are no two or more C5 axes, then are there two or more C4 axis? So again you go to yes. If it is yes, again you ask for I. If I is there, then now you guessed it right, it is octahedral. If it is no, it is O point group. Now if that answer is also no, there are no two or more C4 axis, then the next question is one or more sigma. Okay. If it is no, then you assign it as T point group. If it is yes, then again you ask for, if there is an I, yes, then it's a TH. If it's a no, then it's a TD. Okay. So this section basically covers the cubic point group over here, right? and then you have infinity point groups over here. Okay, so now let's go to two or more C3 axes if it is no. So we'll have to go to next page because this will take entire page. So let's go to two or more C3 axis, and it was no side. So does the molecule contain a proper rotation axis? So that means next question is Cn, whether there is a Cn present or not. Okay, so Cn, if it is a yes versus no. Let's say if there is no Cn axis, then is there any plane? If the plane is there, or if the plane is not there. So you ask the question, sigma is present. If it is present, then you assign it as. So these are, if there is no Cn, then this section will belong to non-rotational point groups, right? So if sigma is absent, then you ask if there is an inversion center. If inversion center is present, you call it as Ci. If inversion center is absent, you call it as C1, right? So basically these three belong to non-rotational point groups. And we have seen here, this thing belongs to, these 7 belong to cubic point groups, right? Okay. So now let's see if Cn is present. Yes, then what happens? Then first you have to identify n, that what is the order of that axis, highest order, and then you ask, are there n C2s perpendicular to Cn? Okay, that is your question. So first step is to identify n, and then second step is n C2s perpendicular to Cn. Okay, so now if that is a yes, then you will ask, does it have a sigma h? Okay, horizontal plane. So horizontal plane meaning sigma h has to be perpendicular to the Cn axis which is present. Okay, now if it is a yes, then you say it's a DNH point group. DNH. Okay, now this has a special case for odd n. If n is odd, the sigmas are called as, there are n sigma v's. Of course there is one sigma h, and then there are n sigma v's are present. And for even n, there are n by 2 sigma v's, n by 2 sigma d's. Okay, this you can confirm by looking at different point groups. Okay, all right. Now let's go to if there is no sigma h. So if there is no sigma h, then does the molecule contain, or let's make some space for that one. Let me write it over here. If there is a dihedral plane of symmetry. Okay, so if it is there, then you call this as D and D point group. Okay, and there would be n sigma d's in this. So this will help you assign how many sigma v's and sigma d's will be present in any particular point group. And if it's a no, if there is no sigma d, then you call it as dn point group. Okay. Also, there is one important point for dnh. If n is equal to 2, so that means there is a C2 axis and there are two C2 axes perpendicular to the original C2 axis. So that means there are three C2 axes which are perpendicular to each other. We have already discussed this case previously. So a C2 axis and there are two C2s perpendicular to each other. So that means all the three C2s lie along x, y, and z coordinates, right? So if you try to put the molecule along the coordinate system, so the three C2s will actually lie along x, y, and z. So in this case, the sigmas can be, or sigmas are called as sigma xy. It is sigma xy, sigma yz, and sigma zx. Because it is not easy to identify which one would you call it as principal axis. So which one would you call it as sigma h versus the two sigma v's, right? So ideally you should have one principal axis out of these three, but then it is not always simple to identify which one is the principal axis. In certain cases, yes, you can do it, but in certain cases you cannot. So the easier way is to call C2 axis as C2z, C2y, C2x, and the planes as sigma xz, sigma yz, sigma zx, instead of calling it as uh, sigma h and sigma v's. Okay, so that helps, but this is only for D2h case where n is equal to 2. This happens because the three C2s are actually perpendicular to each other. This is the only case where it happens that order is same and all three are perpendicular to each other. So that's why there is this confusion. But then you can keep it for your notes. Okay, this information also you may not find in books. This is after several rounds of discussions in class and this thing, so you can keep it for your notes. Okay, all right, so this was yes. So now let's go to nC2s perpendicular to Cn. If there are no such cases, then you will ask if there is a sigma h present, and then if it is a yes, then you call it as CnH. Again, in this case, there would not be any sigma V present in the molecule. Okay. And if there is no sigma H, then you ask if there is sigma V present. And if it is a yes, then you say it's a CnV. And again, for this particular case, for odd n, there are n sigma v's, and for even n, there are n by 2 sigma v's and n by 2 sigma d's. Okay, and if sigma v is not present, then you say that does the molecule contain a 2n-fold improper rotation axis? So you ask if there is any S2n present. If it is a yes, then you call it as S2n point group. If it is a no, then you call it as Cn point group. And that is all. So these are all rotational point groups over here, and then you have dihedral point groups over here. So we have tried to channelize by asking different questions into different streams or different categories of point groups. So now if you notice that it really does not matter whether you are asking whether it's a sigma v or sigma d, right? So in any case, it will be all the sigma v's. For example, here, if you see here, so let's start with here. So you are asking sigma h, which is easy to identify. So you don't care whether it's a sigma v or d. You're worrying about sigma h. Here you're worrying about if there is no sigma h, then uh, any sigma will be present as it can be called as sigma v or sigma d. So it does not, again, it does not matter how do you classify, but then it will be called as sigma d because there are n C2s perpendicular to Cn. That's why it is called as sigma d. Okay, because there is a dihedral, this is a dihedral condition, so that's why there is a sigma d present. Now again, here you are asking sigma h, and if sigma h is not present, then you are asking for vertical plane of symmetry. You don't care whether it's a sigma v or sigma d, it will not change the category of your point group, right? So you can still make no mistake if you accidentally say, see that which one is sigma v or which one is sigma d. The problem is if you do not identify sigma h properly, then you may end up in wrong point group. But if you identify the distinction between sigma h and sigma v, then you're all set. Then there is no problem. Okay. So we have seen how, starting from molecular structure, you can ask several set of questions and arrive at linear cubic point groups, and then uh, these are non-rotational point groups over here, single axis rotational point groups, dihedral point groups, right? So that's very easy, and it should be simple and straightforward. So now let's start practicing. Pick up different molecules, start asking these questions, and see if you can arrive at different point groups. Okay, so I think that's all for today. So, or let me list down certain examples for you, so you can, or you can pick up different examples. So let me just list down certain examples. So you can take water, NH3. Of course, you need to know the structure of this. BCl3. Then you have CH4, CH3Cl, CH2Cl2. Then let's say C6H6 benzene. Then you have PF5. PF5 will be trigonal bipyramidal. Then you have C3H4. Try to work out the structure and then the point group. Then H2O2. Then C2H4. C2H2Cl2, and you can do cis and trans both conformations. Then we have staggered. I have discussed a case of one conformer of ferrocene, right? So, but this one is a different one, staggered ferrocene. And then you can also see eclipsed. We have seen twisted ferrocene, right? Eclipsed ferrocene. And let's say BR. Okay. Also, let's take certain examples of, let's say, letter A, letter E, a sharpened pencil. So a pencil would look something like this, right? if you take the side view, it looks. So I'm trying to give you different shapes just to see if you can actually find out point group. So this is the side view, and then the top view will be something like this, right? The sharpened pencil. So try to find out the point groups of these molecules. So this will give you enough practice by following this set of questions. Okay, so do this in home assignment. So I hope you are really following all the home assignment, because it is important to practice. Otherwise, the things will start to get complex very quickly. And then if you cannot identify a point group clearly, it will be very, very difficult later. Okay. So let's stop today, and we'll discuss in the next lecture. Okay. Thank you.